This section is called Medical Testing and Conditional Probability, Ill or Not. The takeaway for this section is to understand the probabilistic nature of medical test results. Drug or medical tests are an ongoing part of our national conversation. The article below describes how a law requiring welfare applicants to undergo such a test was deemed unconstitutional. Whether in the context of welfare applicants being tested for drug use, Olympic athletes being tested for use of banned substances, or women being screened for breast cancer, medical tests are pervasive in modern society and they have serious consequences. Some might be surprised to learn that medical tests are not as definitive as we might hope. In fact, they typically yield only probabilistic results. A positive result on a medical test for a disease does not tell us for certain that the patient actually has the disease. Rather, it gives a probability that the disease is present. Similarly, a negative result does not guarantee that the disease is not present. The results of medical tests fall into 4 categories. There are true positives, true negatives, false positives, and false negatives. Read the chart below and try to determine which category each of these terms describe. Pause the video while you think about your answer. Then resume the video to check your work. People who indeed have the disease may test positive for it. Because we would consider this test result accurate, we call this category true positives. Unfortunately, people who have the disease may test negative for it. Because we would consider the test results in this category to be inaccurate, we refer to test results in this category as false negatives. Next, people who do not have the disease might test positive for it. Since we also consider these test results to be inaccurate, we call these test results false positives. Finally, many people who do not have the disease will test negative for it. Since we consider test results in this category to be accurate, we call them true negatives. Ideally, we would like our medical tests to be as accurate as possible. Sensitivity and specificity are measures of a test's accuracy. Sensitivity measures the accuracy of a test for the people who have the disease. That is the first column of our chart above. The sensitivity of a test is the probability that the test will detect the disease in a person who does have the disease. Accordingly, the sensitivity measures a test's ability to detect correctly the presence of a disease. Therefore, a test with high sensitivity has many true positives, but relatively few false negatives. If you actually have a disease, a high sensitivity test is very likely to detect it. On the other hand, specificity measures the accuracy of the test for people who do not have the disease. That is, people in the second column of our chart above. The specificity of a test is the probability that the test will give a negative result for a person who does not have the disease. That is, the specificity measures a test's ability to identify correctly the absence of a disease. Therefore, a test with high sensitivity will have many true negatives, but relatively few false positives. If you are healthy and therefore belong in the second column of the chart above, a high specificity test is very likely to confirm that fact. In this section, we will calculate sensitivity and specificity by examining the results of experiments or studies. Recall from the previous section that this is called empirical probability. Moreover, empirical probability is found by taking the ratio of the number of favorable outcomes to the total number of outcomes in the experiment. Since sensitivity measures the accuracy of the test on the first column of our chart, people who have the disease, we will consider only the first column when calculating sensitivity. For the moment, let's forget that the second column exists. This means our denominator is made up of all people in the study who have the disease, the people in the first column of our chart. And our numerator is all the people in this column for which the test is accurate, our true positives. Thus, our formula for sensitivity is true positives divided by all who have the disease. Note that since the people in the study that have the disease are made up of true positives and false negatives, some people prefer to write the denominator as true positives plus false negatives, although either formula will work. Specificity, on the other hand, measures the accuracy of the test on the second column of our chart, people who do not have the disease. We will consider only the second column when calculating sensitivity. So for the moment, I will cover the first column up. This means when we calculate specificity, our denominator is all the people in the study who do not have the disease. And our numerator is all the people in this column for which the test was accurate, our true negatives. Therefore, the formula for specificity reads true negatives divided by all who do not have the disease. Since the people in the study who do not have the disease are made up of false positives and true negatives, if you prefer, you may write the denominator as true negatives plus false positives. With that said, I prefer the first version of both of these formulas and will likely refer to these versions when calculating sensitivity and specificity throughout this section. Let's try an example. Example 1. The accompanying table of data is adapted from a study of a test for tuberculosis, TB, among patients diagnosed with pulmonary TB, that is, a TB infection of the lungs. Use the data in the chart to estimate the sensitivity and specificity of this test. Note that the rows and the columns of this chart represent the same thing as the rows and the columns in the chart on the previous page. The difference is we are now specifying the disease to be tuberculosis. Specifically note that just as before, the people who have the disease represent the first column of the chart, while the people who do not have the disease represent the second column of the chart. Now recall that sensitivity measures the accuracy of the test on the first column of our chart, that is, people who have the disease. Once again, for just a moment, I'll cover up the second column of the chart, so we can focus solely on the first. When we are calculating sensitivity, our denominator is made up of all people in the study who have the disease, the people in our first column of our chart, while our numerator is all the people in this column for which the test was accurate, that is, our true positives. Thus, we estimate the sensitivity of this test as 571 over the quantity 571 plus 259. This equals 571 over 830, which is equal to 0.688 or 68.8%. This means approximately 68.8% of people with TB will test positive when given this test. Next, we will estimate the specificity of this test. To check your understanding, you should pause the video and calculate specificity on your own. When you are finished, resume the video to check your answer. Remember, since specificity measures the accuracy of the test for the second column of the chart, people who do not have the disease, it may help to temporarily cover up the first column so that you could focus solely on the second. Welcome back. Since when we estimate specificity, we are focusing solely on the second column, that is, the people in the study who do not have the disease. Our denominator is made up of the people in the study who do not have the disease. that is the people in the second column of our chart. And our numerator is made up of all the people in this column for which the test is accurate, our true negatives. So when we estimate the specificity of this test, we get 162, the number of true negatives, divided by the quantity 162 plus 8, the number of people in the study who do not have the disease. This equals 162 over 170, which equals 0.953 or 95.3%. This means about 95.3% of people without TB will test negative when given this test. Example 2. A certain test has a sensitivity of 93%. If 450 people who have the disease take this test, how many test positive? Remember, sensitivity deals with the first column of the chart. That is, it measures the accuracy of the test for the people who have the disease. If the sensitivity of the test is 93% and 450 people who have the disease take this test, 93% of them will test positive. 93% of 450 is equal to 0.93 times 450, which is approximately 419. So 419 of the 450 people who have the disease will test positive. That means there's 419 true positives. Note, the calculation of sensitivity and specificity for a medical test requires that we know whether a positive result, for example, represents a true positive or a false positive. This means that we need to be able to determine independently who in the test group is healthy and who is not. For this determination, we need an independent test that can be presumed to be accurate. Such a test is called a gold standard. But a gold standard is very often expensive or difficult to administer, which is why researchers hope to come up with inexpensive and easy to administer tests that have high sensitivity and specificity. If they are successful, they could be used instead of the gold standard.